In this lecture, we will discuss what do you mean by angle modulation and its different classification. So, if you consider the modulator, so for example, I can assume that this is a modulator. So, there will be two input signals. One is known as the carrier signal. So, we will represent the carrier signal as C of t, and another signal is M of t. So, M of t is known as the message signal. M of t is a message signal, and C of t is the carrier signal, which is the high frequency signal. So, message signal is normally a low frequency signal, and carrier signal is usually a high frequency signal. And in the case of analog modulation, the carrier signal is a sinusoidal waveform. So, usually we will write this C of t in a general form. C of t is equal to AC cos theta of t. It's a function of time. So angle we will write in as a function of time. And after this modulation, you will get a signal which is represented as S of t. So this is a modulated waveform. So in this particular case, we will discuss angle modulation means the angle of the carrier signal. So here you can see two parameters in the carrier signal. One is the amplitude and another one is the angle. So here the theta of t is represented as the angle. Now, sinusoidal modulation, or this is a classification of one of the classification of analog modulation. And here we can define this angle modulation like this. We can vary the angle of the carrier signal. So theta of t we can vary with respect to the instantaneous amplitude of the message signal. For example, assume that this is a message signal. It can be a speech signal or a video signal, etc. So I'll draw some random waveform here. So assume that this is a message signal, and this is the carrier waveform C of t. And in angle modulation, the angle of the carrier waveform. So here you can see the angle of the carrier waveform. In this particular case, this is theta of t. Theta of t is varied in accordance with the instantaneous amplitude of the message signal. So this is a voltage which is indicated in the y-axis, M of t. So we'll get the modulated waveform S of t, which is simply the carrier waveform and whose angle is varied in accordance with the instantaneous amplitude of the modulated signal. That's the message signal. And this is known as the angle modulation. In general, this theta of t is written as omega ct plus phi of t. So this is actually the frequency plus phase. So omega ct can be written as 2 pi fct plus phi of t. Means this angle can be varied by varying the frequency or by varying the phase. So there is actually two parameters which actually control the angle of this carrier waveform. So again, this angle modulation can be classified into two subcategory, that is frequency modulation and phase modulation. So if you vary the frequency, there is a change in angle. If you vary the phase, there is a change in angle. So the angle modulation and practical, there is a two types, that is known as the phase modulation and frequency modulation. If the phase of the carrier wave is varied, so this is the phase of the carrier wave. In this particular example, this is phi of t. If phi of t is varied with respect to the instantaneous amplitude of the message signal, then it is known as the phase modulation. And if frequency of the carrier waveform, that is fc, is varied, here it is fc is varied instantaneous amplitude of the modulated signal, that is m of t. Okay. So that is known as frequency modulation. Here it is phi of t. So phi of t is varied with respect to the instantaneous amplitude of the message. So this is basically angle modulation and its classification. And now we'll discuss phase modulation. So before that, I'll write one more point. If you observe this particular equation, theta of t is omega ct plus phi of t. If you differentiate this particular equation, d by dt of with respect to theta, if you differentiate, you will get it simply omega c. And assume that the phase shift is a constant. So if phase shift is a constant, or phi of t is initially 0. Okay, there is no phase shift initially. We can simply write it's omega c. Okay, assume that the phase shift, initial phase shift of the signal is 0. So d by dt of theta of t is becomes omega c, or we can write it simply 2 pi fc. Now we can conclude that if you want to find out the frequency from an angle modulated signal, you need to differentiate the angle with respect to time. So instead of this carrier frequency, I can write instantaneous frequency. So if you want to find the instantaneous frequency, if you want to find the instantaneous frequency of the carrier waveform, angle modulated waveform, we need to differentiate the angle. Similarly, if you want to find out the instantaneous angle theta I of t, we need to integrate the signal from 0 to t, or you can change the variable also, but this is, you can integrate this particular frequency. So if you integrate the frequency, you will get angle. And similarly, if you differentiate this angle, you will get frequency. In order to get instantaneous frequency or instantaneous angle, we need to use this relation. Okay, this will be useful when you define frequency modulation. Okay, now we'll discuss phase modulation in detail. Okay, in phase modulation, so we already mentioned that the carrier signal is of the form C of t is equal to AC cos omega ct plus phi. And we will assume that this phi initially, the phi phase shift of the signal is initially 0. So if you indicate like this, you can write the phase modulated signal, or the theta of t. So I'll write in general form initially. Okay. So we know that the carrier signal C of t is equal to AC cos theta of t, and this theta of t can be written as omega ct plus phi. And assume that initially the phi or the phase shift is 0. So you can write simply theta of t is equal to omega ct. So we need to find the phase modulated waveform. In phase modulation, we will vary the phase of the carrier waveform with respect to the message signal. So this is theta of t, and theta of t is omega ct, and we need to vary the phase of this particular carrier waveform with respect to the message signal. So we can write plus m of t. Okay. So we know that the angle is measured in radians, and here also this omega ct is in radian, and now we can see that the m of t is simply a volt. So we can see that we cannot add these two parameters. Of course, both are in different unit or dimension. So in order to make this in radians, or we need a proportionality constant here. So I will introduce a proportionality constant uh, Kp. Okay. So, and the unit of Kp we can define like this because we need to get radians. So in order to cancel this volt, we can divide with a volt and can multiply with rate. So if you look at this particular equation, now the dimensions are correct. So I will introduce a new constant here, that is Kp, which is known as the phase sensitivity of the modulator. Okay. This is a phase sensitivity of the modulator, or very specifically the phase modulation. And the unit of this Kp is radians per volt. Okay. This is also very important. In most of the exam, they will ask the unit of this Kp. So you can remember this, radians per volt. And here you can see that your phase shift is represented as, or phi of t, the phase shift provided by the signal is simply Kp into m of t. So we can write the phase modulated signal like this: S of t is equal to, or AC cos omega ct plus Kp into m of t. So this is a phase modulated signal. Now we can consider a special case, that is your m of t. Your message signal is a single tone modulation, single tone signal, that is simply a sine signal, okay, or cosine waveform. So we can write am cos 2 pi fm t. That is your message signal as a single tone signal. So this is known as a single tone modulation. So we'll consider a special case. That is the message signal is simply a sinusoidal waveform. In the previous case, m of t can be any signal like m of t can take any waveform. So that's a general case. So we'll call it as a baseband signal. Okay, this is a baseband signal, and in this particular case, the bandwidth of this particular signal can be W. So 0 to W can be the different frequency components available in this particular signal. Now we are discussing a signal and whose frequency is FM. So this is a modulating signal frequency. It's a low frequency signal. There is only one frequency in this particular signal. Now if you substitute here, your equation becomes AC cos omega ct plus Kp into, in place of m of t, you can substitute am cos 2 pi fm of t. Okay. So this is a frequency signal, single tone signal. So this is the equation for a single tone modulation. And if you observe this, here the phase shift is simply Kp into am cos 2 pi fm of t. So from this, you can define one more point, that is phase deviation or maximum phase deviation. So phi of t maximum in this particular case, there is a phase deviation, or we can call it as a maximum phase deviation in the case of singleton modulation. So if you observe this particular equation, the Kp am cos 2 pi fm t, the maximum value of cos is 1. So we can write it simply Kp into am, because the maximum value of cos 2 pi fm t is equal to 1. So we can remember this particular formula. This is also very useful when you do the problems. So maximum phase deviation for a singleton modulation, we can write Kp into Am. Am is the amplitude of the modulated signal, and Kp is the phase sensitivity constant. Okay. Now we can discuss the frequency modulation. In frequency modulation, again, we can write the carrier signal in the general form. C of t is equal to AC cos theta of t, and this theta of t can be written as omega ct plus phi or phi of t, and assume that initially this phi is equal to 0. So in order to make the equation in a simple form, we'll write assume that the initial phase shift of the signal is 0. And one more point you need to remember that if you want to find out the instantaneous frequency from this angle, we need to if you want to find out the instantaneous frequency, you need to differentiate this angle, then you will get a omega I or 2 pi fi, the instantaneous frequency. Similarly, if you want to find out the angle theta of t, instantaneous angle, if you know the frequency, you need to simply integrate this equation. Okay, 2 pi fi, you need to integrate. So now we'll define frequency modulation. So assume that we need to find the instantaneous frequency, and your initial frequency of the carrier is fc from this particular expression, and we need to change this fc with respect to the instantaneous amplitude of the message signal. So you can write fc plus m of t, but we know that the unit of frequency is hertz, and finally we need to get a frequency which is the instantaneous frequency or the FM signal frequency. So the result must be in hertz, but the unit of m of t is usually volt, so the dimension is different. So in order to make this, we need to take another constant. It's a proportionality constant. We can define this constant as kf, and the unit of this particular constant is hertz per volt. Okay. So you can see that the instantaneous frequency fi of t, we can write fc plus kf into m of t. And now we got the instantaneous frequency. So this is the instantaneous frequency. Instantaneous frequency of the FM signal. But if you look at this particular equation, the signal, we need the change in the form of angle because it's cos theta of t. Now we got the instantaneous frequency, that fi of t, but we required the change in terms of angle. And before that, we can define this km, that kf is defined as the frequency sensitivity, and the unit of this particular kf is hertz per volt. This is also very important, the unit of this frequency sensitivity constant. Now, if you want to find out the total change in angle, so this is the instantaneous frequency. To find the change in angle, because here it is theta of t. So we already know, if you know the frequency, you can find the change in angle by integrating the frequency. So we can write this theta of t, it's simply integral of fi of t. Okay. So if you integrate this fi of t, simply 2 pi into this term, that is fi. Fi we can replace by fc plus kf into m of t. Okay, and we can change the variable also, but now I'll write with respect to t itself. Okay, so if you differentiate, if you integrate this, you will get 2 pi into this is fc. So fc is a constant, so you can write fc into t if you integrate the first term. And if you integrate the second term, it's simply 2 pi into kf into integral of m of t dt. Okay. So the angle, total angle variation, you can write theta of t is equal to 2 pi fct plus 2 pi kf into m of t. Now we can substitute this theta of t here. So you will get the frequency modulated signal. So now your carrier signal is changed to frequency modulated signal. You can write AC, there is no change in the amplitude, and cos, it's actually cos theta of t, and in place of theta of t, you can write this. So AC cos 2 pi fct, you can write omega ct plus, and remaining is 2 pi kf into integral of m of t dt. Okay. So this is a FM modulated signal. And now we need to write the special case, that's a singleton modulation. So in a singleton modulation, you can write the m of t. The signal m of t can be written as am cos 2 pi fm t. So instead of m of t, you can substitute am cos 2 pi fm t. Here you can see that in the fm equation, the input signal m of t should be integrated from with respect to t. So we can write the as some, in the case of singleton modulation, you can write AC cos in place of omega ct plus 2 pi kf. In place of m of t, you can substitute am cos 2 pi fm t. And if you integrate this, you will get am becomes sine 2 pi fm t and divided by 2 pi f. Okay. So if you observe this, we'll simply integrate this m of t. So you'll get am sine 2 pi fm t divided by 2 pi fm. And you can see that 2 pi will be cancelled. So 2 pi will be cancelled, and remaining term, it's you can write kf am by f. Okay, so we can give a substitution here, and this kf into am by fm is known as which is defined as modulation index of f. And this kf into am, I'll put one more substitution here, that is delta f, and we will call it as frequency deviation. This kf into am, we can write delta f, and this modulation index usually we will denote it by beta, or we can put beta of f, that is a frequency modulation. And beta I can also write in another form, that is delta f by fm also. So these two equations are very important. when you do the problems in the case of FM signal. So you'll get two relationship for the modulation index. And now we can substitute in the standard equation. So sum will be, sorry, the modulated waveform becomes AC cos omega ct plus beta into or beta f into sine 2 pi fm of t. So this is a final equation for a fm in the case of singleton modulation. Okay. Now we can discuss one more point here, that is the maximum frequency deviation. So we already discussed that Fi in this particular case, singleton modulation, if you write this frequency, instantaneous frequency of the signal from this particular relation, it's Fc plus beta into sine 2 pi, omega c. It becomes omega ct plus kf into am by fm into sine 2 pi fm of t. So this is the frequency, instantaneous frequency of the FM signal for a singleton modulation. And if you write in terms of f, you can write the maximum variation is Fc plus kf into am. Okay, so the maximum frequency variation you can write simply Fc plus kf into am, and this is known as the maximum frequency deviation, and the minimum frequency deviation is Fc minus kf into am. That's a minimum frequency deviation. So this is a maximum frequency deviation, and this is a minimum frequency deviation. Delta kf into af is frequency deviation, kf into am is a frequency deviation, delta f, and we can write Fc plus delta f and Fc minus delta f. And one more thing you need to define, that is a carrier sink. In most of the question they will ask what is a carrier sink in the case of, or we can define in another way, that is a total variation of carrier frequency. The carrier frequency, so we can define as 2 del of f. So there will be two parameters, frequency deviation, that is del of f, and 2 del of f is normally known as the carrier sink or total variation in the carrier frequency. So these two parameters are also very important when you do the problem. Now I think we discussed about theory, and some questions you can expect from directly from this concept. They will ask the unit of kf, kp, etc., and definition like frequency deviation, modulation index, etc. And they will also write sometimes the standard equation, and we need to identify whether it's a PM signal or a FM signal, and for single tone modulation and baseband signal, etc. Okay. Now we'll discuss one problem. So here a frequency modulated carrier is represented by V of t, or V is equal to 20 sine 6.28 into 10 raised to 8 plus 4 sine 6 to 8. So now we need to find the different components. So it is given that it's a frequency modulated signal. If it is a frequency modulated signal, the general form of that particular signal, you can write Fm of t can be written as, or S of t can be written as AC cos omega ct plus beta sine 2 pi fm of t. Okay, so this is the general form, and if you compare with the general form, you can see that so this is the given equation is also in this particular form. So given equation is an fm modulated waveform, fm modulated wave. Now from this particular equation, if you compare, you can find the carrier frequency. So we can find fc, fm, and frequency deviation. And if you compare this equation, you can see that omega c, in place of omega ct, it is written 6.28 into 10 raised to 8. Okay, so this is a frequency in radians per. Now we need to write in terms of hertz. So you can write fc is equal to 6.28 into 10 raised to 8, because omega is 2 pi f. So you can write fc like this: 6.28 10 raised to 8 divided by 2 into 3.14. Okay, so this 3.14 will be cancelled, and you will get 2 here. So 2 will be cancelled. Finally, you will get 10 raised to 8. So we can write 100 gigahertz. That's the frequency of the signal. Okay. So here the unit is radians per second. Now similarly, you can find out omega m. That's a modulating signal frequency, the 2 pi fm of t, or simply it's omega m into t. So that is 6 to 8 in this particular case, 6 to 8 radians per second. So from this you can write fm is equal to 6 to 8 divided by 2 into 3.14. And if you simplify this, you will get 100 hertz. Okay. Now we can find the beta, or frequency deviation. So beta is given by 4. So if you observe here, omega ct plus b beta. So here this is beta. Okay. So you can write it is 4, or you can write there is a relation for beta, that is delta f by fm. So we know fm and beta. So from this you can calculate the frequency deviation, that is 4 into 100. So you'll get 400 hertz. So this is a frequency deviation, and next lecture we will discuss some details about the FM signal, and we'll do more problems.